Okay, so let's just look at some of the notes for section 3.2. And there's two things that we learn in there. Just some facts about derivatives, maybe more important if you're a math major. So what the important fact I think is this there, which is we don't prove. If you actually were a math major and you went on, yeah, you definitely would memorize the proof to this theorem. If f is differentiable at A, then it has to be continuous at A. So remember, if it's differentiable at A, it just means that the limit, we have this difference quotient here, f of A plus h minus f of A over h, that the limit as h goes to 0 from the left is equal to the limit as h goes to 0 from the right. In other words, the limit of that difference quotient as h goes to 0 exists. So f is differential at A, then it's also continuous at A. Okay, but you can take the converse of that. If it's not continuous at A, it cannot be differentiable at A. But there's also a fact, you'll see it kind of demonstrated later on. So just because a function is continuous at A, it doesn't mean it's differentiable at A, right? Not continuous means it cannot be differentiable. If it is differentiable, then it's continuous. But it's not. You can't actually use what's called the contrapositive of this. You can't say that just because a function is continuous at A, that it's differentiable at A. And here's this great example right here, the absolute value. So if you look at this peak right here, the function is definitely continuous there, right? You can just draw the graph without lifting your pencil, but look, remember the derivative is essentially like the slope. And so if you look here at this function, as we go, and I think that's x equal -1, as you go to x equals -1 from the left, the slope is the slope is -1. In other words, the limit of the difference quotient as we go to -1 from the left, the limit of that difference quotient is -1. Now, if we, here on the right side, the slope is 1. So the limit of the difference quotient, if you come from the right, is +1. So, yeah, so if you look again, so if you look at this function, f of x equals x plus 1 plus 2, yeah, you see that the limit of the difference quotient from the left and the right, yeah, are different. So the derivative doesn't exist there, but it is continuous. So again, so let's just go back up here. We learned these really great facts. If f is differentiable at A, then it's continuous at A. If f is not continuous at A, then it's not differential at A. But you cannot make the claim that if f is continuous at A, that it's differentiable at A. And here's a perfect example. Continuous at x equal -1, not differentiable at x equal to -1. And I know there are problems in my lab about this. And again, as an engineer, I'm not sure this is the most important thing in the world to know. Math major, definitely, you definitely want to know that. Here, look at this 2 here. Here's another example of a function that's continuous at, here it's continuous at x equal to 0, but it's not differentiable because what happens is that the slope, this is the cube root of x, and what happens is that the slope of the tangent line at x equal to 0 is actually infinite. Okay, so the limit from the left, we're not going to prove that. The limit from the left is not the same as the limit from the right. Continuous at x equal to 0, the cube root. So it's continuous at x equal to 0, but the derivative doesn't exist there. So here's one. Let's look at one. I guess I'm going backwards, 3, 2, 1. So let's look at this first function here. It's a hyperbola. Vertical asymptote, x equal to 2, right? That's where the point of discontinuity. And as you go to 2 from the left, the denominator is negative. It goes to -infinity. If you go to 2 from the right, the denominator is positive. It goes to +infinity. But the function is not defined at x equal to 2. So the function is not continuous at x equal to 2. And f prime of 2 doesn't exist. Yeah, f prime of 2 DNE does not exist. Okay, so there are problems like that in my lab, and it's more just about, do you understand, just proper use of applying this theorem. I think this is more important or more interesting anyway, probably definitely this is something you want to know. It'll be useful later on for, to be successful at calculus, you kind of have to know this. So now let's look at that function. Let's look at that first function. Look at the one on the left. I'm going to say first one. Which one's the first one? It's this, and let me just erase all this. We'll just start from scratch. And Okay, so the parabola, oh yeah, it is labeled 1 right here. It's a parabola. And so what you can see here is we go from left to right, the graph goes down. Okay, graph goes down, that means the slopes of the tangent or the derivative is negative. When the function's going down, the tangent lines have a negative slope, right? And then you get to the vertex where the tangent line has a slope of 0, and then the function starts going up again. So that means the slope of the tangent line is positive. And what you can see here is that not only as you go from the vertex, I mean, this bottom point, we start going up, not only is the graph going up, it's going up and up at a faster rate. In other words, the tangent lines have a steeper slope. Now, as we go to the vertex from the left, okay, the tangent lines have a negative slope, but it's kind of decreasing negative slope. It's not going down. As we go from left to right, it's going down at a slower rate. So now let's look at the critical thing is, let's graph the derivative right on top of the parabola. Okay, so as we go to x equals -1 from the right, you see that the derivative is below the x-axis. So the derivative, yeah, so it's negative, right? Which means, okay, so which corresponds to the fact that on the left, this has the slope of the tangent lines are negative, right? And you can see here when you get to the vertex, right, the graph of the derivative hits hits the x-axis right there. It's 0, right? These match up. The derivative is 0 there, so the graph of the derivative hits the line y equals 0, and then as we continue to the right, the tangent lines become positive. So now you see that the graph of the derivative is above the y-axis right there. I mean, above the x-axis. It's above the line y equals 0. And it's actually we'll learn later that the derivative of a parabola is actually just it's just a straight line. So you see, so let's just say one more thing here. You see that where the graph of the derivative is below the line y equals 0 or the x-axis. You see how this, as we go from left to right, the second coordinate of the graph of the derivative, well, it's negative, but you see the second coordinates get smaller and smaller until eventually it gets 0, and that corresponds again to the vertex, the place where the parabola changes its direction. And then the coordinates get bigger and bigger and bigger because the tangent lines are increasing at a steeper slope. And you can see the same behavior going on in number 2. This is some kind of cubic. And wherever the graph of the changes direction, you see that the graph of the tangent hits the line y equals 0, right? The second coordinate of the graph of the derivative is 0 at these extreme points right here and here. Okay, and so when the function's going up, we know the graph of right. So here, so the graph in black is the original function, and the graph in blue is the derivative. Okay, so when the original function is going up, we see the graph of the derivative is above the x-axis, or the second coordinate is positive, but it actually might be going down because as the tangent lines become less and less steep, yeah, so the second coordinates of the derivative function get smaller. Okay, and then when the graph starts going down, yeah, the graph of the derivative has to go below the x-axis because the second coordinate is now negative. And then when you get to the second extreme point, yeah, the graph of the derivative, once again, the second coordinate is 0, and then starts going back up. And now as we go to the right of the second vertex, it's going up and up at a faster rate. So we see that the second coordinates of the derivative are increasing. And I think that's the last thing here. Oh, there's a couple more examples right here. Oh, I think this is kind of a fun example. Number 4 here. Okay, so look here. So now that's an absolute value. And so to the left of x equal to 2, right, the slope of that absolute value is -2, right? And then as you get to the right of x equal to 2, the slope becomes just 2. And now let's graph the derivative. Well, the derivative is just to the left of 2. It's just y equals -2, and then the slope of the derivative when we get to the right of 2, well, that's just the line y equals to 2. So I think that's the last example.